Okay, so let's make a tree diagram. There are two events that happen. Two things we were tracking. So what is one of those events that we were tracking? Either you made it or you missed. So that's going to be event. We'll call that event shot, is the way I've been doing it. And so if we start up here, there were two possibilities on the shot.
You're going to make it, you're going to miss.
It was a make or it was a miss. And now what else did we track? What's the other event? It was their gender. So we'll call this one event gender. Again, you don't have to have the name like that, but I'm trying to put those levels in because you guys are so confused by the tree diagram. I'm hoping to try to make you see the levels of it. So out of the people who made it, what was the difference in gender? It could be male or female. And out of the people that missed, it could be any questions on how I made this tree diagram? Okay, we are not completely finished with it though. Because if you leave a tree diagram like this, this means every event is equally likely to occur. That means what's the chances of making or missing? In this case, it would be 50-50. Because I don't have any probabilities on this tree diagram. But looking at the numbers, we know it wasn't 50-50 for make or miss. So what were, let's start with event shot. What's the probability that they make the shot?
23%. 1950. Not 56. Yeah.
It's what?
19 over 81.
Yeah.
It is 19 over 81. So the probability of making a shot here, this would be 19 over 81. And let's turn that into a decimal, because it's going to be a little easier to work with. 0.23. Does everybody understand where this number comes from? This is all of the makes divided by the total number of shots. Now what about here? What's the probability of missing? Well, that would be 62 over 81.
76%. Or 77.
It would have to be 77. Because these represent all the possibilities for event shot. So what do these percentages have to add to be? 100%. That's one. That's all the different possibilities for event shot. Questions on where any of that came from? Now the next one on the tree diagram is a little bit trickier.
Oh, actually, I have a question about that when it adds up to 100.
Mm-hmm.
What if you can round both of them up?
You need to pick one up, one down.
Yeah, one up and one down.
Or just put 5 at the end of both of them. Like go to 3 decimal places. Either way. Okay, so looking at this branch, or these two branches, these are only looking at the people who made it. So I am no longer looking at the misses. It's kind of like a given statement. These branches represent only the people who made it. So looking at the makes, how many were male? Or what percentage were male makes?
13 out of 19.
13 out of 19. And then let's get a decimal for that. 13 divided by 19. Be a little less than 0.7. What is it, 0.6?
0.6.
Okay. Does everybody understand that? That's a little trickier. You're only looking at makes. This is not just everyone, only the makes. Okay, let's look at the second branch there. What would go in the female spot? What proportion of the maids were by females?
6 out of 19.
That would be 6 out of 19.
That's, only 31.
It shouldn't be 0.31
32.
because remember, these two branches are all the possibilities for the makes. So they have to add to be 100% or 1. Any questions where these numbers come from? Okay, now let's do the same with the misses. So now we're only looking at the people who missed. So of the misses, what proportion or what percentage were males? 27 out of 62.
That is, 0.44.
0.44. Okay. Oh, I'm kind of running out of space here. See if I can zoom in. Okay. Can y'all see that? Let me make it a little bold. That's better. Okay, and then out of the people who missed, what proportion were female?
35 out of 62.
35 out of 62, which is 56%. Any questions on the tree diagram, where that comes from? Anybody? So the big key here, what makes them different? These events were not equally likely to occur. That's why we had to put these proportions or these percentages of likeliness. And then remember, once you get to the second event, I need to zoom out a little bit more. Once I get to the event gender, I'm only looking at of the makes. So that's why these turned to 19 in the denominator, because I was only looking at the makes.
So,
It's kind of like a given statement.
how do you tell, like, well, does it matter which order your events go in? Like, what's on top and bottom?
It doesn't. So if you flip the tree diagram, if you went male or female, then I'd have to be finding what percentage is male. That would be 40 out of 81. So you would have different percentages up here. But if I multiplied down the branch, it would still be the same percent likelihood in the end.
Okay.
So that doesn't matter the order of the events.
Okay.
Okay, we're going to use the whole number answers over here. So forget proportions, let's build whole number answers. So remember, with a Venn diagram, everything that's in this circle represents all the made shots. So what's the total number have to be in this circle? 19. So what I like to do is I like to make myself a little note at the top. This has to total to be 19. Right? This circle represents all the females. So what does that circle need to be? 41. Because there's 41 total females. Any questions where those two numbers come from? This whole circle has to be 19. This whole circle has to be 41. Now I would start by finding where do they overlap. So what does this part where both circles are represent?
Females that made a shot.
These are all the females who also made a shot. So I would start by finding that number.
6.
There are 6. 6 females who made the shot. So I know this number, I'm going to use a different color. That number is 6. Now remember, this whole circle has to total to be 19. So if there are 6 females who made a shot, then how many made shots are out here? That means they were not female.
13.
That would be 13. Again, you could just take the total has to be 19, subtract these 6. to find the 13 made shots that were not female. And then I would erase my little note. And then same thing going on here. This has to be all the females, has to add to be 41. There are 6 females who made the shot. So how many females are out here? You could just subtract to find that. And now remember, what does the whole box represent?
Total amount of.
Everybody.
It's everyone in our sample space, or everyone in the universe. So what does this number have to total to be?
81.
Well, in total, everything in the box has to add to be 81.
27.
We have 13, 6, and 35 already accounted for. So we could add those up. 13 plus 6 is 19. 19 plus 35,
54.
54. So if the whole thing has to be 81 and I already have 54 of them accounted for, you could do 81 minus 54, which is 27. And think about it in terms of context. What do these 27 people represent? Inside here, this is everyone who made a shot or is a female. So who are these 27 people?
The males who missed.
The males who missed. It's everyone who's not female and did not make a shot. So this would be the males who missed. It's what's left in the sample space. What is my sample space? So what does sample space mean?
All your outcomes.
The list
Your
of,
possible outcomes.
exactly, the list of all possible outcomes. So we can find the sample space by tracing the tree diagram down. So go down the first branch of the tree diagram. What could happen on that first branch? You could make it and be a male. So that's the first element in the sample space. You go make and male. Okay, what's the next branch?
Make and female.
Okay, if I'm going down our tree diagram we drew together, you're right, that is in the sample space. But the next one would be the make and female, right? If you look at your tree diagram. I can't go back on here. Okay, what would be the next branch coming down?
Miss and male.
Miss and male. And then the last branch.
Miss and female.
I'm having a hard time writing an E. There we go. Any questions on identifying the sample space? That's it. Tree diagram is the best way to find the sample space. Work down the tree branches. All right, I'm going to let you guys, let's try to do 2 through 4. Those are kind of the simple probability questions. I'm going to give you a minute, maybe 90 seconds, to try to do 2 through 4, and then we'll see what we got. Okay. No. So when I look at 2, what's the probability of a shot being made? So how many total shots were there? 81. So that is my denominator, the total possible outcomes. And then the numerator, how many of those were favorable? So how many shots were made? 19. So 2 is correct. 19 over 81. Any questions on 2? What about 3? So 3, we don't see this very often, but we have one here, the little c. What did the little c represent?
Complement.
It's the complement. And so what does the complement mean? If I'm asking for the complement of something.
Opposite.
It's really kind of like the opposite, kind of like saying not. We're really saying everything that's not in shots made. So in this case, the complement of shots made would be the shots missed, because that's everything not inside shots made. So I still have 81 total shots. That's my denominator. And then the numerator then is what's not in shots made. That would be what's in shots missed. That would be 62 over 81. That's correct. Any questions on 3? And then 4, the probability of being female. Again, still 81 total. That's the denominator. The number of females is 41 as the numerator. That would be correct. Any questions on 4? Okay, so some of you guys have already asked me about 5 and 6. But let's go ahead and review what those symbols mean. So the symbol that looks kind of like an N, right? An upside down U. It is like an and statement. That symbol, we call that the intersection. It's where both things are at the same time. That's why we can call it an and statement. So if I'm looking for the probability of shots made intersecting with females, that means these are the people who made a shot and are female. So the denominator, how many total people are there in my sample space?
41.
81. Wait.
You said
How many total people are in the sample space here?
19.
Boy, we're throwing out a lot of numbers.
You're confusing the heck out of me now.
62.
Okay, so let's think about what do we need to happen? We need them to make their shot and be female.
6.
So there are 6 people that did that, but what is my sample space? How many total possible outcomes?
13, 27, 35.
It's just asking.
41.
It's just asking how to make it 13.
I give up.
Hold on.
Don't give up.
Every single number.
81.
So shots made and females that made it as well.
So I have
We only look at the female.
also have another question. So sometimes we restrict our sample space and we look at a subset, right? Only a particular part of the sample space. When does that happen? When do we change the denominator or change our sample
When you're
space?
given.
When there's a
It's
given. When I'm given a condition or I'm given a subset. This is the given condition here. When I have the line here and here. Am I given some condition in 5 or 6?
No.
I'm not. There is no given condition. That means my sample space is still everyone. Doesn't change. So how many total people are in the sample space? There are 81 people in the sample space.
Everybody keeps being.
Yeah, and you were confused just acting like nothing was there.
I didn't say anything. How could I confuse you? I was just looking. Just
The
looking.
face said it all.
So there's 81 total in the sample space. And now how many of those are favorable? They have to meet this condition. Make their shot and be female. 6. So we're good at finding 6. But you guys wanted to change the denominator. Change the sample space. So let's review again. When does that happen? When do we change the sample space?
When there's a given.
When I'm given some condition. Right? That's a subset. I'm looking at just part of the entire sample space. Okay, so on 6, what does this symbol represent?
Or. It's a union.
It's a union,
Oh.
and it is like an or statement. So we can think of that as being or, and we're going to call that symbol, let me do it in red, call that symbol a union. So I'm going to start with here. What would be my denominator?
81.
Oh, Lord.
Oh,
Here we go
but
again.
it's not with a given.
41.
But it doesn't have a
Yeah,
given.
it would.
It's
81.
81. It's
There's not a
81.
given.
There's
so
not a
you don't
given.
change it.
That's correct. It's
I think
81
I-
because
I'm
there
guessing
is...
Basically, especially keep throwing me
Why do
off.
you
So
do
I'm just
that?
like,
Yeah, I mean, I tried to really hammer it home, and you still said
Yeah,
41.
because I'm just throwing out answers. Because you look at us weird whenever we say the right answer.
I look at you weird whether you say nothing or everything. It's nothing different. So if I look at an or statement, so or statements are a little trickier. because I'm looking for everyone who made a shot or is a female. So we don't have a nice column in our two-way table that tells who made the shots or was a female. So does anybody think they know what the numerator is there? Anybody? Let's share them. 54?
I was gonna say
Where did
19.
that come from?
19?
You made the shot or you was a female.
Mm-hmm.
So it had to be those. Either you total up your made shot.
Okay. I agree with that statement. I agree with that statement too. So how many people made a shot?
19 in total.
19. So I counted all of these people.
Yes.
There were 19 people who made a shot. I need to add that to the number of people who are female.
Oh, so 19 plus
60.
21.
So how many people were female?
54.
19 plus 41.
Subtract 6.
60.
That is 60.
Subtract 6.
Why?
Because you can't.
It's the overlap.
Because those are the ones that got counted twice.
I've counted these people twice. They're in both groups. But they can't be counted
Oh,
twice.
okay.
Dang.
Right.
So these 6 have been counted twice. That's the overlap. So I need to add 19 and 41, which is 60, and subtract those 6.
54.
It is 54.
I don't know, like, I didn't even do subtraction, I just did 13 and 41.
You did 13.
And yeah, 41 since 6 was already counted.
That's a way you could do it as well. If you look at your Venn diagram, look back at your Venn diagram you drew. What were we overlapping there? The shots made and females. So let's look at 7. How would we read what we're looking for in 7?
Probability of male given you made the shot.
So the probability the person was male given they made the shot. So I'm given a subset. I'm not looking at everyone anymore. I'm only looking at which portion?
Shots made.
The people who made a shot. I'm not looking at everyone, just the people who made a shot. So how many total people are in that subset? There are only 19 people who made the shot. So my denominator would be 19.
How nervous were you when they?
Did I look real nervous?
Yeah, you was like when we started like saying all the answers, you was like, I'm throwing shots. Like,
No, I knew.
terrified for a solid 5 seconds.
I was
I mean,
good.
You didn't just like pretty much call me ugly earlier. That was the perfect
This the
time
whole
to say that.
student in front of
Oh,
us.
they knew. That wasn't a surprise. They knew.
Yeah, that,
So the given number here, there were 19 people who made the shot. And now, what am I looking for? The number of those that were male. That's the favorable condition. So the probability of a male, given they made the shot, is 13 out of 19. Any questions on 8? Let's look at 8. Now, what's my given condition for 8? That's not my given condition.
Male.
I'm given they're a male. I'm given they have to be male. So my denominator is now 40. And out of those 40,
13.
how many made the shot?
13.
13.
I get everything here, and once it comes to like independent, dependent, I've no.
I'm fixing to do that right now.
I was scared to open my bag of chips in front of them.
That's good. I appreciate that.
I was very scared to eat my
You be in there going,
chips.
I mean, I really appreciate that.
I was intentionally crickling my bag.
9. Is making the shot and being a male, are those independent of each other? And then justify your answer. So here's the 2 things I'm testing. I'm wanting to know, making the shot and being male, are those independent of each other? So here is how you test it. we need to find the probability of one of the events. So which one do you want to find? It doesn't matter.
Making the shot.
So let's find the probability of making the shot.
0.23.
So the probability of making the shot would be 19 out of 81. Which is 0.23. Now, to test for independence, we must find the probability of the same thing. So if I chose the probability of make, I need to find the probability of making again, but I need to be given the condition, given event B, which is they are male. You see how the probability of the event, it's the same event. But this is with the everyone. This is with a subset of everyone. That's how you test for independence. So now what's my denominator?
40.
40. Given they're a male. So my denominator has to be 40. And out of those 40, how many were makes? Made the shot.
13.
Okay. So let's find out what is this decimal. What is 13 out of 40? 0.33. So now, are these two probabilities the same or different?
They're different.
They're different. So because they're different,
No, they're not independent.
they are not independent. If they were the same, yes, they're independent. The tree diagram should look like. All right, for some people, they're still there.
Can I draw it?
There are two possibilities. You could make or you could miss. Are those equally likely to occur?
No.
No.
45%.
45% make.
That's where you put the numbers.
So if only 45% were make, then the probability of making is 0.45. So if you had a 45% chance of making it, what's the percent chance of missing? 55%, because they have to add to be 1. That's the entire sample space.
That makes sense. Makes me feel retarded. It makes sense now.
And now, what could happen? What's the other thing we're tracking? If we made it, what else are we looking at? Rim, no rim.
Hey, I got the diagram now, just didn't get the numbers.
Were those equally likely to occur? No. So on a make, what percent hit the rim? 30. So if 30% hit the rim, what percent didn't hit the rim that were a make? 70. Guys, stop.
That's the same as on the other side?
Well, I don't know. Let's look. For the miss, what could happen when you miss? You could hit the rim or no rim. Now it says the ones that didn't go in, 70% of them missed the rim. So we know 70% were no rim. So how many hit the rim? 30%. That's the tree diagram.
That's what I. Whereas Dylan Ryan was saying.
Okay, well, I got the diagram. I done a lot better than I did last time you did this paper, so. I made progress.
That's good. That's what we're looking for. Progress. All right?
Hit rim. 70%.
Oh my gosh.
So when I'm looking here, what percent hit the rim? So here's how you're supposed to do these. Okay? These are kind of tricky. Here hit the rim. So to get there, we would have to multiply 0.45. Okay, so here is where this gets a little different because we haven't defined probabilities from a tree diagram. We don't have the two-way table. All right, you know you're going to have one on the test like this.
Yeah.
So let's make sure we know how to do it. How can we find the probability of hitting the rim?
Well, it gives it to us because the bottoms are the same.
Right. So this is a special case because right here hitting the rim happened 30% of the time, and right here hitting the rim happened 30% of the time. So because they both agreed, the answer is going to be 0.30. Now, if they didn't both agree, here's what you would have to do. You would have to multiply down the branch. We would have to go from 0.45 times 0.3. You see how I've worked my way down this branch to hit the rim? So that would be, what is 0.45 times 0.3?
0.15.
0.135.
0.14.
Let's just go 0.135. And then, is that the only branch that has hit the rim? No, there's another one here. So I've got to track down that branch, which is 0.55 times 0.3.
That'd be 0.16.
0.165. And now then I would add those together. If they were if they were different, what is 0.135 plus 0.165?
280, 290.
290. Not quite. 0.3. If you add them.
That's what I said.
0.3.
Well, yeah.
Because the fives would round up, so you'd have 3 plus 6 plus 1, which is 0, up again. So 0.3. Does everybody understand how to do that? Look at 2. What's the probability of getting the complement of shot made?
70%.
No.
Shot miss.
55%. Because what is shot made? Shot made is 45. So the complement would be missing. 55%. What's this one say? It needs to hit the rim and not go in. Hit the rim and not go in.
0.3.
No.
0.7.
No.
0.3.
No.
Okay, and did not go in. Shot
Hit the rim
0.7.
and did not go in.
So you gotta multiply.
Yes.
That did not go in for the rim.
Yes.
No rim.
So we would multiply 0.55 times
0.3.
0.3, which we've already done.
12.
Well, no, we've already done it. It's 0.165.
Oh, I added them.
Wait, they didn't hit the rim though.
You see, I had that.
Oh, wait.
right.
These did hit the rim.
Can we play Rocky music?
We need to finish this.
That'd be 17%.
Yeah. 17 or 0.165. Look at 4. What's this saying? What's the probability that it hit the rim or
Didn't go in.
didn't go in?
13%.
So this one's kind of a little different. What percentage did not go in?
Didn't go in.
Didn't 55. So this part did not go in is 55%. Now how many other ones hit the rim? Well, it'd be this branch here.
30%.
Not 30%.
Point.
This whole branch. 0.135. You see how miss is in the first level. That's why I could use just 55%. But because rim is all the way down here in this bottom level, I'm going to have to multiply. 0.45 times 0.3, which is 0.135. And now that we're going to add those together. 0.135 times 0.55, which is 0.685.
Yeah.
Wow.
So the ands and ors, they're hard with a tree diagram, right? They're more difficult. The givens are easier with a tree diagram. So look at 5. This says given, the shot was made. That means I'm only looking here. I'm only looking at this portion. How many of those hit the rim?
30%.
That's it. 30%. So the given statements are easy. There's no multiplying. You just go to that level. 6. What's the probability it hit the rim given They did not make the shot.
So we can-
30.
It's 30% again, where this one, 30%. So is hit rim and shot made, are those independent?
Yes.
They are. Because the probability of hitting rim, given they made the shot, was 30%. And the probability that they hit the rim, given they had the complement of making the shot, was also 30%. So because those match, they are independent.